So we will look at other different techniques to evaluate integrals using tables of formulas, other kinds of formulas, and an introduction to numerical integration. Well, and I mentioned this as an introduction because later on, whether you're a math major or an engineering major, you'll take either numerical methods or numerical analysis, well, depending on the branch you go. So, and you will do a lot of this using a programming language. Could be Python, could be MATLAB, or other languages. I believe Maple, that's another software that is used. All right, so let's look at the tables of integrals. So for tables of integrals, we will be given a formula, an integral, and we will try to look at some formula that we can use to make it work. So instead of going through the process of integration by parts, or what else, trigonometric substitution, or trigonometric integration, partial fraction, well, there's some formulas that in fact all those formulas come from using those methods of integration, so there's a big connection between those. Well, by the way, there's a little typo here. Well, not typo, I'm missing the dx's. So, well, if we look at these integrals right here, the three of them look somewhat similar. All right. And well, for the first integral, x ln x, that's an integral that we did in section 8.2, where when we cover integration by parts. And well, we went over the Liata thing, and to say that u equals the ln part and dv the x dx. Okay. We're not going to go through the integration, so we're just going to identify the type of problem that we're going to do, or the method that we do. And well, for the second integral, we have the integral of ln x divided by x. Well, so let's see. Notice in this case we have this dx over x, which can be helpful to be part of the u du part, right? So in this case, if we said u equals to ln x du, which is the derivative of ln x, which is 1 over x dx, and then we can do just the general power rule and integrate that. All right. But what about this one? Well, so this may not be as easy using the methods that we know. So in this case, we may need other methods, but we'll see. So the idea is that, for example, number one, we are given this crazy looking integral, which of course we could evaluate it using the methods that we know, but in this case we're going to use a table of formulas. And actually, if you look at the last page on your handout, it's fine if you can rip it up so you can have it next to you, so we can identify which formula are we going to use. All right. And well, the real trick here is to try to identify the form, the factor, the type of function that we have, and if anything can be taken as a u du. All right. Well, so in this case, let me see. I don't think so, but I had a few more. So when I look at this integral, well, I will try to find something that contains a natural log over here and being multiplied by somehow a u to another power, so we can use that formula. Okay, let's observe the formulas and see if we can relate that integral with something from that formula sheet. Is there anything? Which one? Number 3? Number 3 looks like a good idea. Yes, so number 3. Well, in this case, what do we have? Well, I know it's not that u won't be just x, because if you observe the pattern, we have a sign to x right here and a sign to x over there. All right. That happens when that is easier to visualize if we rewrite the integral as sine 2x quantity cubed cosine, and I'm going to write it in a different way, by the way. I'm going to write it alright, and in this case here we can see this ln of u to the n, which comes from formula 3. Alright, well, but of course we still need to set a u and a du because we may need a factor to compensate the du part. Well, so let's have a look at that. So u equals to sine 2x du equals the derivative of sine, which is cosine 2x times 2 mini chain rule dx. And if we solve for cosine 2x dx, that equals to 1/2. Alright, so let's rewrite this integral in terms of u. So that's the integral. In this case, this is u cubed ln of u times 1/2 du. Alright, however, what we could do at this point, I guess, is just write down the du and have all these coefficients outside since the very first step of the substitution. That's fine. Alright, now we can compare this with formula 3. Formula 3 tells us that the integral of u cubed ln of u, well, in this case, with this will be, well, 1/2 u to the 3 plus 1 over 3 plus 1 squared times -1 plus n, which is 3 plus 1, n plus 1, which is 3 plus 1, ln of u. Alright, and plus c. In this case, it would be great if we wrote what n is. Okay, so now that we just used the formula, don't forget this factor of 1/2. Alright, so what is 3 plus 1? Isn't that a 4? And a 4 in the denominator, but 4 in the denominators is going to get squared. But that's going to give us a 16. And then that one times 1/2, isn't that going to be a 32? Okay, so that's 1 over 32. U to the 4th. I'm gonna write everything first in terms of u first, and then -1 plus 4 ln of u plus c. And then let's go back to substitute what we got for u, which in this case is 1 over 32 sine to the 4th power of 2x -1 plus 4 ln of sine 2x. And in this case, notice I'm writing absolute value bars for the sine function, because recall the sine function goes between -1 and 1, so it outputs both positives and negatives. Alright, plus c. Final answer. Let's have a look at the next example. So okay, integrate, okay, x times the square root of 5 minus 4x squared. Well, if we had a cubed over here, well, we could have used directly u substitution. I mean, just set up the u du part and then we would be fine. Alright, but it's not the case. Okay, it's not the case, so we may need to look for another formula. So my advice here, every time you have like radicals with pluses and minus, it would be a good idea to write this as something squared minus another something squared, because something that we may see in these formulas, we have those forms essentially. So let me rewrite the integral. Let's write it as x times the square root of quantity squared minus quantity squared. And those quantities are, well, the number whose square is 5. That's root of 5. And the quantity whose square is 4x to the 4th. How about 2x squared? Alright. And let's see, can we find a formula that works to evaluate this integral? If so, which one? Number 5? Looks like number 5, right? Even though that number 5 doesn't have anything outside of the radical. However, by pattern recognition, the u part is 2x squared, whose derivative is 1 degree less, whatever coefficient x to the first power, which is what we have here. So that should work very, very well. So number 5, formula number 5 with, let's see, with a equals to square root of 5 and u equals to 2x squared. Okay, so in this case for the u part, we need to set up du as usual. That's a 4x dx, and x dx equals 1/4 du. Alright. Okay, so let's see, let's write down this integral in terms of u. So this x times dx right here will become our du. That's the integral of the square root of, what is this, a squared minus u squared du, but that times a 4, which I'm going to write outside of the integral. And well, kind of ignore this factor of 1/4 and focus on the integral. Let's write down the corresponding formula in terms of u. That is, in this case, well, that's 1/4 times formula number 5. And looking at formula number 5, that's a 1/2 u root of a squared minus u squared plus a squared arc sine u over a, and the whole thing plus c. Okay, looking at this result, do these results look familiar? They look like those results we got from trigonometric substitution, right? So we could have evaluated this integral using trigonometric substitution. And well, looking at these powers right here, typically that's not like the most straightforward way to think about it. So the first way to think about this one is by looking at a table of formulas, right? So let's substitute what we got for u and what we got for a. But yeah, let me get this 1/4 still outside. So this will be 1/4 bracket, that's a 1/2 u, which is 2x squared, square root of a squared minus u squared, which is the original radical, and plus a squared, but a squared is simply 5 arc sine of 2x squared over root of 5. Alright, and plus c. So let's simplify these coefficients. Well, these two are going to get cancelled, but in this case we will be left with this 1/4 multiplying x squared square root of 5 minus 4x squared. Alright, and then don't forget here to distribute this 1/4 multiplying with the 5, giving us a 5/4. 5/4 times arc sine 2x squared over root of 5 plus c. Alright. So here the idea is to try to compare a given integral so we can make it look like one of these given formulas. So hopefully it works, like in this case. In some cases it's very straightforward. Oh, it looks exactly like this one. However, there's other cases in which we may need to do some work. Okay,
isn't that 1/2 multiplying like the whole thing, not only the difference?
let's see, let me check. Yes, so that should be 5. Okay, let me do a 2 over here, and let me change this for an 8. How about that? All right, that fixes it, I think. So like the next problem, let's see, and it's a problem that we have done before, the x squared minus 6x. So well, in this case we don't have an immediate difference of squares or sum of squares, because on the one hand it is the second term in this case, the one causing a little bit of trouble. Alright, so what we need to do in this case is complete the square, so we can write it as something squared minus something squared. Alright, that completing the square process, I'm going to do it on the side first. So x squared minus 6x, and well, plus something minus something, because if we add a number to complete the square, then we need to do the opposite as well, so we can keep the integrity of the original value. Now we need that magical mystery number that completes the square. What is that number? Let's call it m. All right, and that m is the middle coefficient, which is -6 divided by 2 squared. In this case, -6 over 2, that's -3. And -3 squared is +9. So that's the number that completes the square. Well, from here what we got, it's a perfect square trinomial that we can simply factor the following way. That's the quantity whose square is x squared, simply x, the sign of the middle term, and square root of the third term. In this case is 3, the whole thing squared. Alright, and by the way, I sent you a video on how to factor these perfect square trinomials using those formulas, and then just -9. Okay, so let's go back to the integral. That's the integral of 1 over the square root of x minus 3 quantity squared minus 9, alright, dx. Now that we have this integral, let's see if there's anything that looks like any of the formulas from here. If so, which one is it? Formula 6? Looks like formula 6. Yes. Looks like formula 6, where, well, we still need to set the u, and the a. So in this case, u equals x minus 3 du is simply the x, which is great. But in this case, a equals 3, and a squared, of course, is 9. Alright, so let's write this in terms of u du first. That's always my advice, write it in terms of u's, and then write down the corresponding formula still in terms of u, and then back substitute. Of course, after some practice with this, you may be able to even doing this in your head and not write the whole thing, but that's my advice. Okay, so that's the integral of the square root of u squared minus. Okay, here I have a little issue. Sometimes my a's look like 9, so hopefully this one is clear. And well, the integral of du over the square root of u squared minus a squared is simply ln of u plus the square root of u squared minus a squared plus c. And of course, that's an integral that also comes from using what's this called? Trigonometric substitution, right? So let's see, what's next? Back substitute for u and a squared. So ln of u, which is x minus 3 plus the square root of x minus 3 squared minus a squared, which is 9, plus c. Okay. And of course, guys, I mean, this table of formulas that I just gave you, which is about half a page, it's basically nothing. I mean, there's actually books that are dedicated to just formulas of integrals, series, transforms, tables. Actually, I forgot to bring that book. I have a book which is this thick, actually, with I don't know, with like 8,000 formulas that are for any other more advanced integration techniques. But of course they are really nice, organized. Like, okay, Calc 1, Calc 2 type of integrals that are used in special functions like the gamma function, alpha and beta function. Those are from advanced engineering courses. Transforms like the Laplace and Fourier transform that you will learn later in differential equations, and some graphs I'll bring next time so you can have a look at that book. All right. Well, so this concludes the using tables of formulas to integrate functions. So we're going to go to the numerical approximations, and well, of course, we are going to take a few steps back to what we learned back in Calculus 1 when you first got an overview of what the integral is using Riemann sums. And well, the idea relied on partitioning a given curve, a given function, into rectangles. Well, first you did a baby example with partitioning some region into 4 rectangles. Well, I mean, just to see an approximation, because of course, keep in mind that the actual value of an integral relies on adding the area of infinitely many rectangles within the given range. But of course, do you have time to evaluate infinitely many areas? Come on, that's not possible. So that's why we use limits at infinity with Riemann sums, which give rise to the integral. So let's go back to what Riemann sums were. And it's good to revisit this so you can see the comparison with the 2 methods that we're going to learn in this class, which number 1 is the Trapezoid Rule and the other one is the Simpson's Rule. So let's see. So let's approximate the area rounded to 3 decimal places of the region bounded by f of x equals e to the negative 0.1 x squared, and bounded by the lines x equals to 1 and x equals to 3 and the y-axis. All right, using 4 left endpoint rectangles of equal width and 4 midpoint, well, it's supposed to be midpoint, mid-endpoint, yes, mid-endpoint rectangles of equal width. So, and this picture will come, when it comes here, so it will look familiar. So number 1, let's see where everything goes wrong. So when we want to integrate e to the negative 0.1 x squared dx, well, unfortunately, we are missing a factor of x that stands the du part of the problem. So for this reason, we cannot use any of the methods that we know so far. All right. So, and just briefly talking about this integral. This looks like the integral of e to the negative x squared. For those of you who have taken a statistics course, this is the integral that gives rise to the normal distribution. And what's it called? But of course, you don't get to evaluate this integral. You're just given a table, or you just use the normal CDF command on your graphing calculator. However, we will learn how to evaluate an integral like this in Calc 3 using polar coordinate transformations to polar coordinates. When it comes to, actually, this is double integrals using polar coordinates. Later in differential equations, you will see how this integral, I know the connection is weird. This is connected to n factorial, to the factorial of a number, and then this is also used to find the factorial of 1/2, which is also weird to be the square root of pi. I don't know, it's just so crazy connections that out of an integral that we cannot evaluate, we get with this result that the factorial of a number, which is technically supposed to be a rational number, we get a square root of an irrational number. But you will see this wonderful result when you take differential equations. In the meantime, let's approximate this integral by just adding the formulas, by just adding the rectangles. And well, this gives rise to the following graph. So let's see. It looks like the bell curve. So that's why I mentioned the the normal distribution looks like a bell curve, but I'm gonna redraw this picture because I only want the area between 1 and 3, and I need something easier to look at. All right, so in this case, from 1, 2, 3. All right, so we want this area right here, and we need to subdivide this into 4 rectangles of equal width. All right, that means you might remember this formula, the delta x formula, which is b minus a over n, where b is the upper limit and a is the lower limit, and n is the number of rectangles that we want to subdivide this region. That is, in this case, b minus a, where this is 3 minus 1 over n, which equals to 4, that's 2/4, and which reduces to 1/2. That is, every width of this rectangle here will be, so 1, 2, 3, so that's going to be another rectangle. So that's 1, 2, 3, 4. All right, so let's see. So that's 1.5 and 2.5. Okay, and now be careful here, because in this case we want the left endpoint. So for the left endpoint we are going to consider okay, so this is the area that we are approximating, and well, as you can judge from the picture, look at these areas of the rectangles. They're even outside of the region that we want to find the area for, so that's not going to give us an accurate result. That's why we want infinitely many of those. So let's see. So clearly here our delta x right here, the increment or the length of the rectangle is 0.5, of course. So let's see what can we do about this. So what we're going to do to find the area, that means integrate from 1 to 3 e to the negative 0.1 x squared dx. And well, in this case we cannot evaluate the integral, but what we're going to do is find the area of every single rectangle, and in this case, well, this will be f of 1 times the x plus f of 2, oh, not f of 2, f of 1.5, and actually it's not dx, it's delta x, because it's the approximation, plus f of 2 delta x plus f of 2.5 delta x. All right, so we want only the left endpoint, right, the area to the left of the region. Well, of course, that means that we will have to evaluate. Okay, let me do some factoring in here. Notice the GCF here is the delta x, and I will be left with f of 1 plus f of 1.5 plus f of 2 plus f of 2.5. All right, and of course in this case delta x is a number that we know, so I'm going to replace that delta x with simply 1/2. All right, and in this case, well, we need to do f of 1, f of 1.5, f of 2, f of 2.5, which is where the tedious part is going to be. So okay, you don't need to write this. So if we were to write all this by hand, it would have been e to the negative 0.11 squared plus e to the negative 0.1 times 1.5 squared. So imagine having to type all these quantities on the graphing calculator. Even writing them themselves, it's already something, isn't it? So I'm going to show you a command on the graphing calculator so you can do these calculations a lot easier. Okay, number one, let me do something really basic, like f of x equals 2x plus 1. What is f of 1? To get f of 1, what we need to do is evaluate 1 wherever we see the x. That is 2 times 1 plus 1, which is 3. Alright? Yes? Yes. So let's see. Okay, let me move to the graphing calculator. Okay. Perfect. And no, we're not going to type every single operation on the graphing calculator screen. So number one, let me clear this. What was the example I gave you? So number one, y equals to 2x plus 1. All right. Notice this function that I just typed is labeled under y1. Do we agree with this? Okay, I'm going to quit here. Second quit. And I'm gonna go, where is it? Okay, I'm gonna go vars, because that's where the variables are. Our function that we type contains variable. Go to vars, and then click 1 to the right to the y vars, and then function is highlighted. Click enter there, and we will select our y1. So y1, open parentheses, type the number 1, which is what we did before. That is, we're evaluating the given function we just typed at x equals to 1. And that's the result that I got by hand initially. Alright. Let's evaluate. Okay, vars, right, enter, select y1. And let me find y of 5. Okay, if we did this by hand, that would have been 2 times 5, which is 10, plus the other one, that's 11, right? There it is, our 11. And this is a lot shorter than actually having to type every single function. We just take advantage of this yvar command, so we can just do our calculations a lot easier. Okay? So, okay, let me clear all this, and let's go with the actual function that we want. Okay, so in this case, what we got, so that was second ln to get the exponential function. That's negative, was it a 0.1? Negative 0.1 x squared. All right, so that's our function. That is our function. And well, in this case, we're done with typing the function. This is what I'm going to do. So coming back from the notes right here. Okay, so that's, let me erase this. I'm going to go from here to the final result. I'm going to do 1/2. And I'm going to open parentheses. I'm going to go vars, y vars function, our function y1, which is our exponential function that we just typed. Enter, open parentheses to evaluate it at 1. Close parentheses. Plus vars, do the same, to evaluate it at 1.5. Close parentheses. Be sure to close parentheses after yes.
An easier way to type y1 is you hit alpha and then trace, and all your y values are there.
Yeah, but the thing is, those tracing is going to give us approximated values, and if we do it right here on the graphic, I mean in this part of the screen, we just get straight to the final result.
It's still on the same part of the screen. It's just to type off the y1. It's a shortcut.
That's y1. Where under?
You hit alpha.
Alpha.
And then trace.
Where is alpha? Oh, alpha and trace. Oh, yes, that's another one. Thank you. Okay, let me clear because. Thank you. Yeah, that way I don't have to go through the menu, right? Thank you. I didn't know that one. Okay, let me delete. Okay, so, okay, alpha, trace, nice. Okay, now. Plus alpha, trace, enter, much better. And then the next value that we valued is a 2. And plus alpha, trace, y1 of 2.5. Oops, I forgot parentheses. Close parentheses, and I'm going to close another parenthesis for the whole expression. And what are we going to get? Just click enter. That's 1.454467, but in this case we'll round to 3 decimal places. 1.454 is fine. Well, actually it's not equal, it's approximately 1.454. All right, and let me erase this so it doesn't confuse anyone. All right, okay, 4 mid-endpoint rectangles of each of equal width. Well, in this case we need to find the midpoints of every single point that we have labeled for the x's. That is, in this case, the midpoint between 1 and 1.5, we obtain it by adding 1 plus 1.5 and divided by 2. So let me use a different color here. That would be 1.25. This would be 1.75. This would be 2.25. And last but not least, 2.75. So we're going to repeat the calculation with midpoints this time, but in this case we are going to do we're just going to change these values. All right. So let me again set this up. Area, which is the integral from 1 to 3 e to the negative 0.1 x squared dx, equals well, instead of writing all these many delta x's, I'm just going to write 1 and f of not 1 this time because we're starting to use the midpoint. That's how f of 1.25 plus f of 1.75 plus f of 2.25 plus f of 2.75. All right. Let's do this in the calculator. Okay, so let me clear everything. So I'm going to do 1 over 2 and open parentheses for the whole expression inside of the parentheses, and alpha trace, enter, because that's our y1, evaluated at 1.25 plus alpha trace, enter, 1.25, 1.75, and plus alpha trace, enter, open parentheses, the next value is 2.25, close parentheses, plus alpha trace, enter, open parentheses, and 2.75. Close parentheses for the evaluation, close parentheses for the entire expression, and click enter. And well, we get 1.331, which rounds up to 1.332, which is close to the previous value, to the value that we got for left endpoint, but it's not quite the value. I mean, of course, it's an approximation, and of course, it's also a very lame approximation because just for rectangles, look at the picture. Look at the amount of area that are being overestimated in the different setups. So that's a 1.332. All right, close to the previous value, but that's fine. And well, in this case, we would have gotten a part C to have right endpoints. So for right endpoints, we take the right values, that is evaluating the function at 1.5, 2, 2.5, and 3. But we're going to skip that part. So the idea was just to remind a little bit what the Riemann sums are for left endpoints, and well, this is technically not a Riemann sum, it's just finding the area using areas of rectangles. Okay, so the trapezoid rule. So for the trapezoid rule, the idea is that we use, okay, let me change the perspective of the picture first. That way it's easier to explain the formula. So in this case, we have a base 1, which is technically a height 1 if we put it in that perspective, but I'm going to stick to the original letters. And the height right here, which is technically the length. Alright, so in this case, well, the area for the trapezoid, that you might remember from basic geometry, that's 1/2 base 1 plus base 2 times the height. Alright? And well, the picture below, it's going to give us an idea of how the trapezoid rule is going to give us a lot better approximation of the area as opposed to finding areas using rectangles. So here, look at all these little gaps right here that are left by these rectangles. Now, if instead we use trapezoids, see these little areas right here are a lot much smaller than these little areas that are left out due to the rectangles. So in this case, we would expect to have a more accurate result using the trapezoid rule instead of finding areas of rectangles as before. Alright, and well, so there's a little formula that we need to keep in mind right here. So it's very similar. However, the difference here is delta x divided by 2, and for all the computations that we do for every, well, in this case not rectangle, but rather every trapezoid, it's only the first one and the last one, the ones that are not multiplied by 2, but the ones in the middle, they get multiplied by 2. Alright, and again, this delta x equals b minus a over n is the same. That's to find the length of, or rather, yeah, the width of the, what's it called, the trapezoid in this case. So in this case, what we're essentially doing is finding the area under a curve by finding multiple areas under straight lines. Do you see this straight line right here? Do you see that straight line right there? And then if we had another one right here, well, that another straight line right here, and that straight line, it's closer in accuracy than just that horizontal line given by the height of the rectangle right here. So let's see, let's do one example, and let's use 4 trapezoids of equal width to approximate the area of the region from example number 4. That is the one from the previous page. And let me, that's fine. All right, so in this case, let me draw the graph real quick. 1, 2, 3, 4. So we want this area with 4 trapezoids. Alright, that means we want the area of this trapezoid plus the area of that trapezoid and the area of that trapezoid and that area of that trapezoid. Alright, 4 trapezoids. And same values, 1, 1.5, 2, 2.5, and 3. Okay? So, number 1, the area equals the integral from 1 to 3 e to the negative 0.1 x squared dx. But in this case, we're not going to use the areas of this rectangle, but we're going to use the areas of the trapezoids in this case. And we are going to find these ones right here, delta x over 2, and that's going to be f of 1 plus f of 2, or rather 1.5, plus f of 2 plus f of 2.5 plus f of 3. And I'm missing something. Did you notice what am I missing here? The 2's. So it's only the first term and the last term that are not being multiplied by 2, only the middle ones. So be very careful when putting this on the graphing calculator. Alright? So let's go back to the graphing calculator. The good thing is that we're going to deal with the same function. And delta x, in this case, it's the same one, it's a half. So let me do some simplification first. So delta x, which is 1/2 over 2 times this whole evaluation here. Okay, but 1/2 over 2, doesn't that reduce to 1/4? Okay, so let's simplify this at the same time. That's a 1/4, and well, we're going to change that in our graphing calculator. Okay, so let's do this over here. Let me clear, and well, so that's 1/4, open parentheses. So alpha trace enter, evaluated at 1, close parentheses, plus 2 times, be careful, be sure to write that 2, alpha trace enter, evaluated at 1.5, and plus alpha trace enter, that's 2, close parentheses, plus 2 times alpha trace enter 2.5, close parentheses, plus, in this case, that's the last term that we type rather, that's the y1 evaluated at 3. But in this case, that one doesn't get multiplied by 2, so be careful with this one. And I believe I didn't multiply 1, right? Second insert 2. You can just use the insert function to, instead of deleting everything. And that's alpha trace enter 3, and close parentheses for the whole expression. What? Did I?
Yeah, the very end when you close the 3, you could have.
Okay. Oh yes, I didn't open parentheses, right, for this one.
You also have a beginning that's one of
Mm-hmm. Oh yes. Okay, so I need to. Yeah, all right. Should be this. 1.329. That's 1.330. I mean, it's close to the value that we worked before with using areas under rectangles, right? So yeah, so for this type of problem, it's mostly how to efficiently use the graphing calculator. Thank you, Anna, for this shortcut. It's better than going through the whole menu. Didn't know this one. And